Before we jump into implementing interp, let's do the usual thing of looking at examples. So here is an example for our old interp. This one takes an expression and an environment and nothing else and returns a value. So if we were interpreting just the expression 5, we get just the value 5 out. But now our interp takes a store argument. So if our whole program is just the number 5, we start out not only with the empty environment but also with the empty store. And then, well, we can't just return a value num5. Certainly that should be part of the result. We should still get a 5 back, but we need to get a full result back that is num5 paired together with the new store. Now, just evaluating a 5 doesn't change the store. So that's why when we pass an empty store, we get the empty store back out, paired together with v cross s. That's our one constructor for the result data type. So this now is a complete example for our new interpreter. It's the example of evaluating 5 to get 5, which has no effect on the store. Let's look at another example. Suppose our whole program is box of 5, which when we parse it, we have a box E of num5. The way we interpret this, given the empty store, because we're starting out the program, is we're going to get back a v star s. We're going to get some combinations of a value back and a result back. As we said earlier, when you evaluate just a box expression, you should get a box value out. So it's going to be some sort of box v. And as we evaluate the sub-expression, num5 here, we should get a numv back out. So we know there's going to be a numv5 somewhere. But this numv5 is not going to go inside the box v. The 5 is stored in memory, right? So it needs to be in the result store part. That's why I've written it down here. We're going to have to put it at some cell. So let's say that box allocates cell 1. We're going to make our allocator just start at 1 and count up to the next available spot. So this will be right for this example. Since we're not doing anything else, it's the first thing we're allocating. It'll be at cell 1. And then what the box v has inside of it is that location 1. It doesn't get the value 5 in it. The 5 is stored in memory, but the box v needs to say which piece of memory it corresponds to. And it does that by referring to the allocated location 1. That means that our value data type is going to have numv, close v as before, and now box v has not a plate box, because we're not going to use plates, boxes, or state. It has a location inside of it, which remember is just a number. So it's a box v wraps an address, and the only thing you can do with a box v is go look at that address or change the value at that address. So that's why we have box v1 and cell 1. The 1 has to be the same number because that's the number we just allocated and we want to refer to that allocated spot. But this cell goes in the overall store by adding to the empty store. Empty store because that's what we started with, and then override store because that's how we map a new cell value into the store. Let's look at one more example, a set box example. So just switch to parse mode here, but we have a sub-expression box 5 and 6. Starting with the empty store and environment, and we should get back a value and a store back. Remember that we said we're changing setbox. Unlike plate, curly is going to return this new value as a result of setbox. So whatever else goes on with this example, we should get a numv6 out as the n, because that's the value we just put in the box. Along the way, we must have evaluated this box of 5 expression. And we saw previously, in our previous example, what that should do. We should end up with an override store, cell 1 numv5 empty store along the way. That's what will have happened inside of setbox by the time we've evaluated the sub-expression, and by the time we evaluate this one too. We've got a 6, and we've got a box v1 that refers to that location. So setbox's job is to change this 5 to a 6. But the way we're going to represent stores right now is we'll actually represent the entire history of memory. So we started out with the empty store, we mapped 1 to 5, and the job of setbox is to change the mapping at location 1 to 6. And we do that by just wrapping another override store around it. When we're looking for the value of a box, when we're doing an unbox, as long as we start from the beginning and find the first mapping for a location, we'll get the most recent one, which is the right one, just like happens with environments. So that's a complete example for our new interpreter for setbox.